There is a number so large that the human mind was never designed to hold it: 46 billion light years. That is the radius of the observable universe. The full extent of everything that light, traveling at 300,000 kilometers per second for nearly 13.8 billion years, has had time to reach us from. Not the size of the universe itself, the observable universe. The slice of existence that physics, and only physics, has permitted us to witness. Beyond that boundary, space continues, likely forever. But no signal, no photon, no gravitational ripple has had sufficient time to cross that distance and arrive here, at this pale blue dot, in time for any human to register its existence. The cosmos does not ask for our permission to be incomprehensible. For decades, cosmologists operated under a working assumption. The early universe, the universe of the first few 100 million years after the Big Bang, should have been a relatively simple place. A dark, rapidly cooling, hydrogen-dominated void, punctuated by the first tentative clumps of matter slowly, painfully slowly, collapsing under gravity into the first primitive, chaotic protogalaxies. Dim, diffuse, unstructured. That was the model. That was the consensus, refined across generations of observation, encoded in textbooks used at Cambridge, Caltech, and the Sorbonne alike. The James Webb Space Telescope looked at that early universe, and what it found was not a dark, primitive void. It found cities, not metaphorical cities. Fully structured, gravitationally organized, chemically complex galaxies, enormous, luminous, and incomprehensibly mature, existing in a period when, according to every validated theory of cosmic evolution, they had absolutely no right to be there. In January of this year, NASA confirmed the observation and spectroscopic verification of a galaxy designated MOEM-Z14, with a cosmological redshift of 14.44, meaning its light has been traveling through expanding space for approximately 13.5 billion years, reaching us from a universe only 280 million years old. 280 million years. On a cosmic timeline that spans nearly 14 billion years, that is the equivalent of looking at a photograph of a human being and finding them fully grown, walking and speaking 11 days after conception. The physics does not permit this, and yet, there it is. To understand why this single confirmed observation sent shockwaves through the entire field of observational cosmology, it is necessary to understand what astronomers were actually expecting to find, and why their expectations were not idle speculation, but the product of over a century of increasingly precise and mutually reinforcing scientific discovery. The story begins, as it almost always does in cosmology, with light. When you look at the night sky, you are not seeing the sky as it is. You are seeing it as it was. Light moves fast, 300,000 kilometers per second, the absolute speed limit of the universe. But space is inconceivably large, and even at that velocity, light takes time to cross it. The light arriving in your eye from the moon left its surface approximately 1.3 seconds ago. The light from the sun departed 8 minutes and 20 seconds before it touches your retina. The nearest star to our own solar system, Proxima Centauri, is 4.2 light-years away, meaning the light it emits takes 4.2 years to reach Earth. Scale that out. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, a structure containing roughly 1 trillion stars, sits 2.5 million light-years from Earth. The light arriving from Andromeda tonight left that galaxy 2.5 million years ago, at a time when early Homo species were still figuring out stone tools on the African savanna. Every telescope, without exception, is a time machine. The farther it looks, the deeper into the past it sees. This is not a limitation of technology. It is a consequence of the fundamental physics of the universe. This insight, radical when first grasped, now routine for any first-year astrophysics student, is what makes an instrument like the James Webb Space Telescope so scientifically extraordinary. Launched on December 25, 2021, and placed at the second Lagrange point approximately 1.5 million kilometers from Earth, Webb was engineered from its conception to be the deepest-looking instrument humanity has ever constructed. Its primary mirror spans 6.5 meters in diameter, composed of 18 interlocking gold-coated beryllium hexagons, and is designed to detect infrared radiation, the stretched, red-shifted light of the most distant ancient objects in the cosmos. Why infrared? Because of a phenomenon called cosmological redshift. As the universe expands, the space through which light travels expands with it. A photon emitted by a galaxy in the very early universe begins its journey as visible or ultraviolet light. But as space stretches over billions of years, the wavelength of that photon stretches too, sliding down the electromagnetic spectrum from visible light through infrared and, for the most extreme distances, into microwave wavelengths. To observe a galaxy that existed only 280 million years after the Big Bang, you are not looking for visible light. You are looking for faint, cold infrared radiation stretched across nearly 14 billion years of expanding space. That is what Webb was built to detect. That is the specific physical problem it was constructed to solve. Before Webb, the most distant confirmed galaxy humanity had observed was GNZ11, identified by the Hubble Space Telescope. It existed approximately 400 million years after the Big Bang. Remarkable as that was, cosmologists were comfortable. The timeline still made sense. Galaxies that far back were faint, small, and relatively simple, consistent with theoretical models of how structure forms under gravity in a young universe. Webb shattered that comfort almost immediately after it opened its eyes. The standard model of cosmology, known technically as lambda CDM for lambda cold dark matter, is not a casual framework. It is the product of decades of cross-disciplinary refinement, tested against data from the cosmic microwave background radiation, the thermal afterglow of the Big Bang itself, imprinted on the sky at a temperature of approximately 2.7 Kelvin, from the distribution of galaxy clusters across hundreds of millions of light years, from measurements of the universe's expansion rate, and from the nuclear physics of the first 3 minutes of cosmic time, when hydrogen, helium, and trace lithium were forged in conditions of unimaginable temperature and density. Lambda CDM makes specific, quantitative predictions about how structure grows in the universe. Gravity, working on tiny quantum fluctuations in the early universe, fluctuations imprinted during a period of exponential expansion called inflation, which occurred in the first unimaginably small fraction of the first second of existence, slowly amplifies those irregularities. Matter flows into the densest regions. Gas clouds form. Stars ignite. Over hundreds of millions of years, those first stars, blazing with the fury of pure hydrogen and helium fusion, begin to cluster. Galaxies coalesce around halos of invisible cold dark matter. And over time, those galaxies grow, merge, accumulate heavier elements forged in stellar cores and scattered by supernova, and gradually come to resemble the structured, chemically complex galaxies we observe in the modern universe. Slow, incremental, governed by gravity. That is the prediction. The problem Webb is raising, with compounding, accelerating urgency, is that the universe, in its earliest observable chapters, appears to have ignored it entirely. The galaxy MOMZ14 does not merely exist at a redshift of 14.44. It is bright. Unusually, inexplicably bright. Its luminosity implies a stellar mass, a total quantity of stars, that should not be achievable in only 280 million years of cosmic time, even under the most optimistic assumptions about early star formation efficiency. It contains, according to spectroscopic analysis, nitrogen, a heavy element that is only produced through multiple generations of stellar evolution. Stars form, live, and die, scattering the elements forged in their cores. Then new stars form from that enriched gas. Then they too live and die. The nitrogen in MOMZ14 implies that entire stellar generations have already risen and fallen inside a universe barely 280 million years old. To place that in terms the human nervous system can process, the entire span of time from the Big Bang to the moment MOMZ14's light was emitted is roughly equivalent to the time between the formation of Earth and today, 4.5 billion years, compressed by a factor of 16. In that sliver of cosmic time, a galaxy the size of a mature structure had not just formed, but had already lived through entire stellar dynasties. The question this raises is not one of data interpretation or measurement error. The teams working with Webb's NIR-SPEC spectrograph are among the most rigorous in the world. The redshift of Z equals 14.44 has been confirmed spectroscopically, not merely estimated from photometry. Pascal Oesch of the University of Geneva, co-principal investigator of the survey, stated plainly, "The light is confirmed, the distance is confirmed, and the implications are real. Something happened in the first 300 million years of the universe that the standard model does not account for. And MOEM Z14 is not alone. Since Webb began its deep field surveys, dozens of unexpectedly massive, unexpectedly bright, and unexpectedly chemically evolved galaxies have been found at redshifts that push them back to within the first 500 million years of cosmic time. Each one individually might be dismissed as an outlier, a statistical fluctuation, an anomaly at the edge of the model's predictive range. But collectively, they form a pattern that is growing with every new Webb observation, every new confirmed spectroscopic redshift, every new dataset released from surveys like JADES, the JWST Advanced Deep Extragalactic Survey, and Cosmos Webb, the largest general observer program in Webb's history. There is a popular misconception worth addressing directly here. When astronomers say the universe is approximately 13.8 billion years old, many people instinctively picture a sphere of that radius, 13.8 billion light years from edge to edge. The logic seems simple. If the universe is 13.8 billion years old, light has had 13.8 billion years to travel, so the farthest visible object should be 13.8 billion light years away. That logic is wrong. Space itself has been expanding the entire time. A photon emitted by a distant galaxy shortly after the Big Bang has been traveling through space that is simultaneously stretching. The galaxy that emitted that photon has been carried further away by the expansion of space while the photon was in transit. The result is that the proper distance to the edge of the observable universe today is not 13.8 billion light-years. It is approximately 46.1 billion light-years, the full radius of the observable cosmos, known as the photon horizon. The galaxy JADES GS Z14-0, confirmed by Webb in early 2024 at a co-moving distance of 13.5 billion light-years, has a proper distance of 33.8 billion light-years from Earth today because space continued to expand while its light crossed it. The universe does not respect the simplicity of our intuitions. And at the edge of what we can see, at the boundary of the photon horizon, 46.1 billion light-years away, something deeply unexpected may be organizing the structure of everything within it. What is pulling an entire catalog of galaxy clusters in one specific direction across more than 2.5 billion light-years of space, with a force that no known structure inside the observable universe can account for? The name they gave it carries a weight that most scientific designations do not. MOEM Z14. The MOM stands for Mother of All Miracles. That is not a marketing choice. That is what the researchers themselves wrote in their paper, a spectroscopically confirmed galaxy at redshift 14.44, existing only 280 million years after the Big Bang, confirmed by Webb's NIR-SPEC instrument, and published in the Open Journal of Astrophysics in January of this year. Rohan Naidu of MIT, leading a team of 45 co-discoverers, called it a cosmic miracle. Those are not the words scientists typically reach for. 45 researchers. A single faint smudge of infrared light. The process of confirmation took longer than the detection itself. Webb's NIRCam camera first picked up MOM Z14 as an object that simply vanished, disappeared completely, when observed through filters sensitive to shorter wavelengths. This disappearing act is not a glitch. It is one of the most reliable signatures in observational cosmology, a phenomenon called the Lyman break. Every galaxy emits ultraviolet radiation produced by young, hot stars. But neutral hydrogen, the most abundant element in the universe, absorbs that ultraviolet radiation almost perfectly. A galaxy at extreme redshift, surrounded by and embedded in the neutral hydrogen fog of the early universe, will have all of its ultraviolet light absorbed before it can travel far. The result is a galaxy that appears to simply switch off below a specific wavelength threshold, like a signal that cuts out at a certain frequency. The higher the redshift, the further that cutoff point slides toward the infrared. MOM Z14's cutoff point sat deep in the infrared, consistent with a redshift of approximately 14. That photometric estimate triggered the follow-up observation that changed everything. Webb then turned its NIR-SPEC spectrograph, arguably the most scientifically powerful instrument currently operating in space, toward the target. NIR-SPEC does not simply collect light. It disperses it, spreading it across a detector like a prism, spreads white light into a rainbow, allowing astronomers to read the precise chemical and physical fingerprint encoded in every photon. Each element in the periodic table emits and absorbs light at specific unique wavelengths, a spectral signature as distinctive as a fingerprint. By identifying known emission and absorption lines in a galaxy's spectrum and measuring how far those lines have shifted toward the red end of the spectrum relative to their rest wavelengths, astronomers can calculate the precise redshift, and therefore the precise distance and look-back time, of any object in the sky. The spectroscopic confirmation returned a redshift of 14.44, not estimated, not approximated from color alone. Confirmed line by line in the galaxy's own light. The previous record holder was Jade's GS Z14-0, confirmed at a redshift of 14.18, corresponding to a look-back time that placed it approximately 290 million years after the Big Bang. MOM Z14 pushed that frontier back by another 10 million years. 10 million years sounds like a rounding error when the total age of the universe is 13.8 billion years. But in the context of early cosmic structure formation, 10 million years is geologically significant. It is a full additional epoch of stellar evolution, gas dynamics, gravitational collapse, and chemical enrichment. Or rather, it is 10 million years in which none of those things should have been able to produce what we are actually seeing. MOM Z14 is compact. Its radius spans approximately 300 light-years. For comparison, the Milky Way's disk extends roughly 52,000 light-years from edge to edge, making our galaxy over 170 times wider. Despite that compactness, MOM Z14 contains a stellar mass equivalent to approximately 100 million solar masses, comparable to the Small Magellanic Cloud, the dwarf galaxy currently orbiting the Milky Way. And it is not sitting quietly. At the moment its light was emitted, it was in the middle of a violent burst of rapid star formation, stellar nurseries igniting across its 300 light-year body at a rate that left its surrounding interstellar medium partially ionized by the sheer torrent of energetic photons pouring out of newborn stars. It is small, ancient, furious, and chemically impossible. That last word requires precision. MOM Z14's spectrum revealed the presence of nitrogen. This is the detail that stopped the team cold. Not the distance, not the luminosity, but the nitrogen. Nitrogen is not a primordial element. The Big Bang produced hydrogen, helium, and trace amounts of lithium. Everything heavier than those three elements, every carbon atom in every living cell, every oxygen molecule in every breath ever drawn on Earth, every iron atom in every blood cell of every human being, was forged inside stars, through the nuclear reactions that power stellar cores for millions or billions of years and then scattered across space when those stars died. Nitrogen specifically is produced through the CNO cycle, the carbon-nitrogen-oxygen cycle, a series of nuclear fusion reactions that occur in stars more massive than approximately 1.3 solar masses. In those stars, carbon, nitrogen, and oxygen act as catalysts in the conversion of hydrogen into helium, cycling through the reactions and emerging unchanged while releasing the energy that keeps those stellar cores from collapsing under their own gravity. The nitrogen in MOM Z14 spectrum was not produced in the Big Bang. It was produced inside stars, stars that lived, fused, and died before the galaxy that Webb observed had finished forming. That means stellar generations had already turned over inside a universe 280 million years old. To appreciate what this demands of the timeline, consider the life cycle of a high-mass star. A star of 10 solar masses lives for approximately 20 million years before it exhausts its nuclear fuel and explodes as a core-collapse supernova, seeding the surrounding gas with the heavy elements forged in its core. For MOM Z14 to contain detectable nitrogen enrichment, stars must have formed from primordial gas, lived their full lives, died in supernovae, and enriched a new generation of gas, and that second-generation gas must have then collapsed and begun forming the stars Webb is observing, all within 280 million years. Under the lambda CDM model, this timeline is not comfortably tight. It is broken. MOEM-Z14 is not a data anomaly that emerged from a single observing program. It was discovered through a survey called Cosmos Webb, one of the largest programs ever approved for Webb observation time, a systematic mapping of a patch of sky in the constellation Sextans covering approximately 0.6 square degrees, designed specifically to study the large-scale structure and galaxy population of the early universe. The survey is ongoing. MOEM-Z14 was found within it. The implication is immediate and uncomfortable. If a galaxy at redshift 14.44 was detectable in a survey covering less than 1 square degree of sky, the early universe likely contains a far larger population of such objects waiting to be found across the remaining 41,000 square degrees of the full sky. The numbers that astronomers have been quietly passing around in preprints and conference talks are staggering. Before Webb's launch, theoretical models predicted that galaxies at redshifts above 10 would be rare, faint, and sparse, present in numbers consistent with the slow, gravity-driven growth of structure in the early universe. What Webb has found instead is a population of luminous galaxies at these extreme redshifts that exceeds those theoretical predictions by a factor of approximately 100 times more abundant than expected. The standard interpretation of 100 times more abundant is not that the observations are wrong. Webb's detectors are calibrated to extraordinary precision. The spectroscopic redshifts are confirmed through multiple independent emission lines. The photometric selection is validated. The excess is real, and it has been reproduced by multiple independent teams using different analysis methods across different survey fields. What it means is that one of 3 things is true, and possibly all 3 simultaneously. Either star formation in the early universe was dramatically more efficient than current models allow, meaning gas collapsed into stars at a higher rate than the physics of turbulence, radiation pressure, and magnetic fields in those models predicts. Or the initial fluctuations seeded by inflation were larger than the cosmic microwave background suggests at the scales relevant to early galaxy formation, a possibility that would require significant modification to the inflationary model. Or there is an additional physical mechanism operating in the early universe, perhaps related to the behavior of dark matter, or to a period of early dark energy, or to primordial black holes acting as seeds for accelerated structure formation, that the standard model simply does not include. Each of those possibilities, if confirmed, represents not a correction at the margins of cosmology, but a fundamental revision of the framework. The chemistry of MOEM-Z14 adds another dimension to this problem. Its nitrogen-to-carbon ratio is elevated in a specific way, matching the chemical signature observed in globular clusters, the ancient, densely packed spherical collections of hundreds of thousands to millions of stars that orbit the outskirts of galaxies like the Milky Way. Globular clusters have long been known as some of the oldest stellar structures in the universe, thought to have formed in the earliest epochs of cosmic structure. Their chemical anomalies, elevated nitrogen, unusual sodium-oxygen anticorrelations, have been one of the enduring unsolved problems in stellar astrophysics for decades. The fact that MOEM-Z14, at redshift 14.44, displays the same nitrogen enrichment as these ancient relics in our own galactic neighborhood suggests a direct physical connection between the formation mechanisms of the earliest galaxies and the globular cluster systems we observe billions of years later. The two mysteries, the unexpected abundance of luminous early galaxies and the chemical peculiarities of the oldest star clusters in the modern universe, may be different faces of the same underlying process. A process that happened in the first 300 million years of cosmic time at temperatures and densities so extreme that every nuclear reaction, every gravitational collapse, every stellar ignition proceeded at rates the current models fundamentally underestimate. MOEM-Z14 is not the end of this record-breaking sequence. NASA has stated explicitly that it fully expects this redshift record to be broken again as Webb's surveys continue. The Nancy Grace Roman Space Telescope, NASA's next major space observatory, is designed in part to conduct wide-field surveys that will map the galaxy population across hundreds of square degrees. transforming the handful of confirmed extreme redshift galaxies currently known into a statistical sample large enough to directly test and constrain the competing theoretical models. But here, in the data already in hand, a question is forming that no current model satisfactorily answers. If galaxies this massive, this chemically enriched, this luminous already existed 280 million years after the Big Bang, what seeded them? What collapsed fast enough, hot enough, and dense enough to build stellar dynasties in a universe that, by all rights, should still have been dark? The answer may not be inside the observable universe at all. The universe did not begin with galaxies. It began with a scream. In the first fraction of the first second after the Big Bang, a period measured not in seconds or milliseconds, but in units so small they require scientific notation to express, the entire observable universe was compressed into a region smaller than a proton, at temperatures exceeding 10 to the power of 32 degrees Kelvin. The laws of physics as we currently understand them break down completely at that moment. General relativity, quantum mechanics, thermodynamics, every framework humanity has constructed to describe reality loses its predictive power at the Planck epoch, the first 10 to the power of negative 43 seconds of existence. What triggered the Big Bang, what preceded it, or whether the concept of before even has physical meaning in that context, remains genuinely unanswered. What physics can describe begins a fraction of a second later. By 10 to the power of negative 36 seconds after the Big Bang, the universe entered a period called inflation, a phase of exponential spatial expansion driven by a hypothetical quantum field called the inflaton. During inflation, the universe expanded by a factor of at least 10 to the power of 26 in an almost incomprehensibly short interval. To place that in terms of scale, if a single hydrogen atom were inflated at the same rate for the same duration, it would emerge larger than the entire observable universe. Inflation is not merely a detail in the cosmological timeline. It is the mechanism that seeded every structure that has ever existed, including MOMZ14. Here's the physics of how. Quantum mechanics dictates that no field can be perfectly smooth. At the smallest scales, quantum fluctuations, spontaneous probabilistic variations in energy density, ripple constantly through every field in existence. During inflation, as the universe expanded exponentially, these quantum scale fluctuations were stretched to cosmic scales. A region of space that was slightly denser than its surroundings by a factor of 1 part in 100,000 became, after inflation, a slightly over-dense patch of the early universe, spanning what would eventually become millions of light years. Those density fluctuations, frozen into the fabric of space by the end of inflation, became the seeds of all future cosmic structure. Every galaxy cluster, every filament of the cosmic web, every galaxy, every star, every planet traces its existence back to quantum noise amplified by inflation in the first trillionth of a trillionth of a trillionth of a second. The cosmic microwave background is the fossil record of those fluctuations. Approximately 380,000 years after the Big Bang, the universe had cooled sufficiently to approximately 3,000 Kelvin, roughly the surface temperature of a red dwarf star, for electrons and protons to combine and form neutral hydrogen atoms for the first time. Before this moment, the universe was opaque. Photons could not travel freely. They were constantly scattered by the plasma of free electrons filling all of space, like light scattering inside a dense fog. When neutral atoms formed, the fog cleared. Photons streamed freely for the first time, carrying with them a precise thermal imprint of the density fluctuations present at that moment. Warm spots where matter was slightly denser, cool spots where it was slightly more rarefied. Those photons, stretched by 13.8 billion years of cosmic expansion from visible light down to microwave radiation, form the cosmic microwave background that NASA's WMAP satellite and ESA's Planck satellite mapped with extraordinary precision in the 21st century. The amplitude of those CMB temperature fluctuations, 1 part in 100,000, defines the initial conditions of the universe. It sets the pace at which gravity can amplify density contrasts into bound structures. And in the standard model, that pace is slow enough that building a galaxy as massive and chemically enriched as MOMZ14 in only 280 million years is essentially prohibited. The problem runs deeper than just initial conditions. After recombination, The moment neutral hydrogen formed, the universe entered a period cosmologists call the cosmic dark ages. For perhaps 200 million years, no light-emitting structures existed. The universe was a cold, dark, expanding sea of neutral hydrogen and helium gas, threaded by invisible filaments of dark matter defined by the density fluctuations seeded during inflation. Gravity worked in silence. Slowly, imperceptibly, dark matter, the non-luminous, non-baryonic substance that comprises approximately 27% of the total energy content of the universe, began pulling baryonic matter, ordinary atoms, toward the denser nodes in its filamentary network. Dark matter is not a speculative addition to the model. Its gravitational effects are measured with precision across independent methods. The rotation curves of spiral galaxies, gravitational lensing of background light, the growth rate of galaxy clusters, the acoustic oscillations in the CMB power spectrum. Something massive and non-luminous structures the universe on large scales. Its exact particle identity remains unknown. The leading candidates, weakly interacting massive particles or WIMPs and axions, have not been directly detected in laboratory experiments despite decades of search. But the gravitational evidence for dark matter's existence and its role in seeding cosmic structure is overwhelming. In lambda CDM, dark matter halos, gravitationally bound clumps of dark matter, form first, along the skeleton defined by the cosmic web. Baryonic matter, gas, flows into those halos under gravity. When the gas density and temperature within a halo reach a critical threshold, it fragments and collapses into stars. The minimum halo mass capable of supporting star formation is constrained by the Jeans mass, the critical mass above which a gas cloud's self-gravity overcomes its thermal pressure, and it begins to collapse. For primordial gas at the temperatures of the early universe, the Jeans mass corresponds to structures of roughly 1 million solar masses. Those first collapsed objects, called mini-halos, were the cradles of the very first stars. The first stars were not like the sun. They were monsters. Population 3 stars, as they are classified, formed from gas that contained only hydrogen, helium, and trace lithium. The primordial composition produced during Big Bang nucleosynthesis in the first 3 minutes of cosmic time. With no heavier elements present, the gas cooling mechanisms available to primordial clouds were dramatically less efficient than in later epochs. Modern star-forming molecular clouds cool efficiently through the emission of radiation from carbon monoxide, water, and silicate dust. Primordial gas had none of those coolants. It could only radiate through the less efficient transitions of molecular hydrogen. The result was that primordial gas fragments needed to be much more massive before gravity could overcome thermal pressure, meaning the first stars that formed were dramatically more massive than typical stars today, possibly ranging from tens to thousands of solar masses. A star of 1,000 solar masses burns its nuclear fuel with ferocious intensity, living for perhaps 2 to 3 million years before detonating as a hypernova, an explosion releasing 10 to 100 times the energy of a standard core collapse supernova. These first stellar deaths were the universe's first heavy element enrichment events, seeding the surrounding gas with oxygen, carbon, nitrogen, and the first traces of elements heavier than lithium. The transition from the first generation of stars to the second generation, enriched by the metals scattered by population 3 supernovae, defines the beginning of the process by which galaxies build chemical complexity. But 2 to 3 million years per stellar generation, repeated across enough generations to produce the nitrogen signature in MOMZ14, within a total available window of only 280 million years, requires the entire process to have been running at absolute maximum efficiency from the very first moments of the Dark Ages. Every generation of stars must have formed, lived, and died with minimal delay. Supernova feedback, the powerful outflows of energy and matter that supernovae inject into surrounding gas, must not have expelled that gas before subsequent stellar generations could form. The dark matter halos must have been massive enough, early enough, to retain gas against those feedback processes. Every parameter in the chain must be tuned to its maximum. The physics of supernovae feedback is, in fact, one of the central unsolved problems in galaxy formation theory, precisely because it operates in a regime where the relevant physical scales span more than 15 orders of magnitude. The processes that trigger a supernova occur in the iron core of a dying star, in a region spanning kilometers. The shockwave that results propagates outward through the stellar envelope over hours and days, eventually driving a blast wave through the surrounding interstellar medium over thousands of years, depositing energy and momentum across scales of hundreds of light years, and ultimately influencing the gas dynamics of an entire galaxy spanning tens of thousands of light years. No single simulation can resolve all of those scales simultaneously. Every model that attempts to describe early galaxy formation must make choices about how to represent the effects of supernova feedback below its resolution limit. And those choices profoundly affect what the model predicts about early galaxy masses and luminosities. The factor of 100 excess in luminous early galaxies that Webb has revealed may partly reflect a systematic error in how existing models treat this feedback. Several theoretical teams have already proposed modifications. One class of models suggests that in the early universe, where the gas density was much higher and the interstellar medium was more turbulent, supernova shockwaves were rapidly decelerated by the dense surrounding medium, dissipating their energy locally rather than expelling gas from the halo. This feedback-reduced regime would allow star formation to proceed at dramatically higher efficiency than in the modern universe, potentially explaining a significant fraction of the excess luminosity Webb is observing. Another class of models invokes a more exotic mechanism: the early formation of massive black holes, seeded either by the direct collapse of primordial gas clouds at temperatures above 10,000 Kelvin, bypassing normal stellar evolution entirely to form black holes of 10,000 to 100,000 solar masses directly, or by the remnants of population 3 hypernovae. These massive black holes, accreting gas rapidly in the dense early universe, would power active galactic nuclei, quasars, that could heat and compress surrounding gas into star formation at rates far exceeding what gravity alone would drive. Crucially, the ultraviolet radiation from these early quasars would also contribute to the process of cosmic reionization. The gradual ionization of the neutral hydrogen that filled the universe during the Dark Ages, driven by the accumulating radiation from the first stars and black holes until, by approximately 1 billion years after the Big Bang, the intergalactic medium was fully ionized. MOMZ14 spectrum shows evidence of a partially ionized environment surrounding the galaxy at redshift 14.44. The neutral hydrogen fog of the Dark Ages had already been partially cleared in its immediate vicinity, suggesting that MOMZ14 itself, or a population of similar objects clustered near it, was actively contributing to the ionization of the local intergalactic medium. A galaxy 280 million years old, already enriched with nitrogen, already forming stars at a violent rate, already punching ionized bubbles through the neutral hydrogen of the early universe. The Dark Ages were not as long or as dark as the models predicted. At the very edge of what Webb can currently detect, a question has quietly crystallized into the defining problem of observational cosmology. The physics of inflation, dark matter, primordial nucleosynthesis, stellar evolution, supernova feedback, and black hole formation all converge in the first few 100 million years of cosmic time. And MOMZ14 is revealing that their combined effect was not what the models computed. Something ran faster, something ran hotter. Something reached higher efficiency in those first 300 million years than any simulation has yet reproduced. And Webb, still in the early years of its operational life, is pointing its golden mirrors deeper with each new survey cycle. The record will fall again. The question is not whether another galaxy will be found at redshift 15 or 16 or beyond. The question is what it will contain, and whether what it contains will require not a revision of the model, but its replacement. The survey was called Mirage or Miracle. That name was not chosen casually. When Rohan Naidu and his team at MIT's Kavli Institute for Astrophysics and Space Research first identified the candidate object in the Cosmos Webb survey data, the honest scientific response was not excitement, it was skepticism. The photometric redshift estimate, the initial distance calculation derived from the object's colors across multiple infrared filters, placed it at a redshift of approximately 14. That number sat so far beyond the established frontier of confirmed galaxies that the team's first obligation was not to announce a discovery. It was to design a rigorous program to determine whether what they were seeing was real. Hence, Mirage or Miracle. Either this was a real galaxy at the edge of the observable universe, a cosmic miracle, or it was a mirage, a photometric contaminant, a foreground object whose colors mimicked the signature of an extreme redshift source through some combination of unusual stellar populations, dust attenuation, or instrument artifact. Both possibilities demanded the same response: spectroscopic confirmation, line by line, wavelength by wavelength, with no room for ambiguity. Webb's NIR spec instrument was allocated the observing time, and the spectrum came back unambiguous. The redshift is 14.44. Confirmed. The specific details of what NIR spec returned in that spectrum constitute, in the careful language of peer-reviewed astrophysics, a set of results that are simultaneously groundbreaking and deeply puzzling. The team identified multiple emission lines, the spectral fingerprints of specific atomic transitions, all consistently shifted to wavelengths corresponding to a redshift of 14.44. The most critical among them was the detection of a nitrogen emission line. In the spectrum of a galaxy, emission lines arise when electrons and atoms transition from higher to lower energy levels, releasing photons at precisely defined wavelengths. The presence of a nitrogen emission line in MOMZ14's spectrum is not merely a chemical curiosity. It is a direct, quantitative measurement of the galaxy's nitrogen-to-carbon abundance ratio. The team measured that ratio as greater than 1, a supersolar nitrogen-to-carbon ratio, meaning MOMZ14 contains more nitrogen relative to carbon than the Sun itself does. The Sun formed 4.6 billion years ago, from gas that had been enriched by approximately 9 billion years of prior stellar evolution across the Milky Way. MOMZ14 achieved a supersolar nitrogen-to-carbon ratio in 280 million years of total cosmic time from a universe that began with zero nitrogen whatsoever. The word impossible is not used in published astrophysics papers. The word used instead is tension. The tension here is severe. The leading theoretical explanation the Discovery team put forward is not one that any model predicted before Webb began returning data. It involves a class of stars that, until recently, existed only at the fringes of theoretical astrophysics. Supermassive stars. Not massive stars. Not even the most massive stars currently observed in the modern universe, which reach upper limits of approximately 300 solar masses. Supermassive stars, in the theoretical framework now being invoked to explain MOMZ14, are objects potentially exceeding 10,000 solar masses. Stellar structures so extreme that their interiors operate under physical conditions qualitatively different from any star that has ever been directly observed. In stars above approximately 100 solar masses, the standard nuclear burning physics begins to give way to pair instability processes, a regime where the photons produced in the stellar core carry enough energy to spontaneously create electron-positron pairs, robbing the core of the radiation pressure that supports the star against gravitational collapse. This pair instability triggers pulsations or complete explosive disruption of the star. But in theoretical supermassive stars of 10,000 solar masses or more, operating at core temperatures and densities far beyond the pair instability threshold, a different nuclear burning regime may dominate. The hot CNO cycle operating at such intensity that the nitrogen production rates per unit time exceed anything achievable in standard massive star evolution by orders of magnitude. These theoretical supermassive stars would be extraordinarily short-lived, burning through their fuel in perhaps a few million years or less, but during their brief existence, they would be the most luminous and most chemically productive objects in the universe. Their deaths, in gravitational collapse rather than explosive disruption, would seed the surrounding interstellar medium with a chemical signature dominated by nitrogen overabundance, precisely matching what NIR-spec detected in MOMZ14's spectrum. The connection to globular clusters is direct and experimentally grounded. Decades of high-resolution spectroscopy of individual stars in the Milky Way's ancient globular clusters, objects like Omega Centauri, 47 Tucanae, and NGC 2808, have revealed that a subset of their stellar populations carries exactly this same chemical signature: elevated nitrogen, sodium-oxygen anti-correlations, and helium enrichment that cannot be explained by normal stellar evolution.
Theorists have long suspected that the first generation of stars in globular clusters included objects of extraordinary mass. the so-called polluter stars that chemically enriched the gas from which subsequent stellar generations formed. For decades, this remained an inference drawn from the chemical fossils preserved in ancient stellar spectra, with no direct observational window onto the epoch when those polluter stars actually existed.
MOMZ-14 may be the first direct observation of that epoch in action. As Rohan Naidu himself stated after the confirmation, astronomers can take a page from archaeology and look at the ancient stars in our own galaxy like fossils from the early universe. But with Webb, they also have direct information about galaxies during that time, and the two lines of evidence are converging. The unusual nitrogen enrichment found in MOMZ-14 matches the patterns preserved in the oldest stellar fossils inside the Milky Way. The early universe and the ancient components of our own galaxy are not separate subjects of inquiry. They are the same story, observed from two different vantage points across 13 billion years. The survey data surrounding MOMZ-14 adds another dimension to the picture. MOMZ-14 was not found in isolation. The Cosmos Webb field in which it was identified contains a statistically significant overdensity of other faint, high redshift galaxy candidates in its vicinity, a suggestion that MOMZ-14 may reside within an early protoclusters, a region of space where the density fluctuations seeded during inflation were large enough to drive the formation of multiple massive structures simultaneously in close proximity. Protoclusters in the modern universe eventually evolve into galaxy clusters, the largest gravitationally bound structures in existence, containing hundreds to thousands of galaxies, vast reservoirs of hot intracluster gas, and dark matter halos of up to 1,000 trillion solar masses. If MOMZ-14 sits within an early protocluster, then what Webb is observing is not merely the most distant individual galaxy ever confirmed, but potentially the earliest detectable seed of a structure that will spend the next 13 billion years assembling into one of the universe's most massive objects. The implications for the Standard Model compound at every level of analysis. A confirmed galaxy at redshift 14.44, embedded in a protocluster environment with supersolar nitrogen enrichment, near zero dust attenuation, evidenced by its blue ultraviolet spectral slope of approximately -2.5, and a partially ionized surrounding intergalactic medium in a region where every existing rionization model predicts essentially 100% neutral hydrogen. Each of those properties individually would be noteworthy. Together they describe an object that the Standard Model not only failed to predict, but actively predicts should not exist in its observed form. Jacob Shen, a postdoctoral researcher at MIT and a member of the Discovery team, stated the situation plainly. There is a growing chasm between theory and observation related to the early universe, which presents compelling questions to be explored going forward. The word chasm is significant, not discrepancy, not tension at the 2 sigma level. A chasm, a gap that is widening with each new confirmed detection, each new survey field, each new spectroscopic observation. What makes the MOMZ-14 discovery a genuine inflection point in the history of observational cosmology, rather than simply another record-breaking detection, is the specific combination of what it is and when it exists. Previous record-holding galaxies, while impressive in their distance, were faint, small, and chemically simple enough to be accommodated with varying degrees of strain within the existing theoretical framework. Jade's GS Z14-0 at redshift 14.18 was already deeply challenging to the models. But MOMZ-14 at 14.44 is not simply 10 million years more extreme in look-back time. It is chemically enriched beyond what standard models allow, embedded in a partially ionized region beyond what reionization models allow, and luminous beyond what galaxy formation models allow, simultaneously in the same object. 3 independent violations of the model. 1 galaxy. The discovery was made possible by a specific strategic decision in how Webb's time was allocated. The Cosmos Webb program, spanning approximately 255 hours of Webb observing time, the largest single program in the telescope's history, was designed from the outset to balance area coverage against depth, prioritizing the detection of rare luminous objects that narrower deep fields would miss through sheer probability. MOMZ-14 is a luminous galaxy, It was detectable precisely because Cosmos Webb covered enough sky area to include it. A deeper but narrower survey might never have captured it at all, and the record might still stand at redshift 14.18, while a galaxy at 14.44 sat undiscovered in an unobserved patch of sky. The universe does not volunteer its secrets. They have to be systematically hunted. And the hunt has produced something that the builders of the Standard Model, the architects of Lambda CDM, the theorists who spent decades refining the physics of inflation and dark matter and cosmic reionization, did not build into their frameworks. Supermassive stars, burning with impossible nitrogen-forging intensity inside a galaxy that had no right to exist, at an epoch when the universe had barely finished its first blink, and all of it sitting in a region of space that was already, inexplicably, running ahead of the timeline that every model on Earth had agreed upon. The record will fall again. Webb's mirrors are still turning. What they find next will either close the chasm or split it open entirely. The number that defines MOMZ-14's position in scientific history is deceptively simple, negative 20.2. That is its absolute UV magnitude, a measure of its intrinsic luminosity in ultraviolet light, corrected for the expansion of the universe and expressed in the standard photometric units astronomers use to compare objects across cosmic time. Negative 20.2. It is a number that, stripped of context, means nothing. Placed in context, it is the most scientifically consequential measurement made by the James Webb Space Telescope since first light. A galaxy at redshift 14.44, a galaxy existing only 280 million years after the Big Bang, has no right to be luminous at all. It has no right to be detectable. The theoretical prediction for a typical galaxy at this epoch, derived from the Standard Model's treatment of structure formation under Lambda CDM, is a faint, compact, chemically primitive object straining at the detection threshold of the most sensitive infrared instruments ever built. A galaxy at the lower edge of what Webb could theoretically resolve after weeks of deep integration time. MOMZ-14 was found in a survey image, not a dedicated deep integration, a wide-field survey mosaic. Its UV luminosity exceeds what the models allow, not marginally, not at the 2 sigma level where cosmologists can invoke statistical fluctuation and move on. Its luminosity, combined with its stellar mass, its chemical enrichment, its partially ionized surrounding environment, and its morphological compactness, places it in a regime the models simply did not populate. A region of parameter space that Lambda CDM, as currently formulated, predicts to be empty at this epoch. Empty. And yet there it is. The physical structure of MOMZ-14 itself, resolved by Webb's NIRCam imaging with a pixel scale of 30 milliarcseconds, corresponding to approximately 98 parsecs per pixel at the galaxy's redshift, is as extreme as its chemistry and luminosity. The team modeled the galaxy's light profile using a Bayesian-fitting framework called ForceFo, which simultaneously fits point-spread function-convolved Sirsic profiles to the galaxy's emission across all infrared filters in which it is detected. The result is unambiguous. MOMZ-14 is compact to a degree that sits outside the standard size luminosity redshift scaling relations observed for all other known galaxies at comparable epochs. Its circularized effective radius, the radius enclosing half the galaxy's total light, is 74 parsecs, with an uncertainty of plus or minus approximately 13 parsecs. Its semi-major axis spans 147 parsecs. For comparison, the molecular cloud complex W51 in the Milky Way, one of the most massive and active star-forming regions in our own galaxy, spans approximately 150 parsecs. MOMZ-14, in its entirety, is approximately the same physical size as a single giant molecular cloud complex in the modern Milky Way. Inside that 150 parsec body, the equivalent of 100 million solar masses of stars are burning. The stellar surface density, the mass of stars per unit area, implied by those numbers is extraordinary. Compressing 100 million solar masses into a sphere of 150 parsec radius produces stellar densities comparable to those found in the cores of the most massive globular clusters in the modern universe. This is not a coincidence the Discovery team has dismissed. It is, in fact, the physical basis for the supermassive star hypothesis. In environments of extreme stellar density, the rate of stellar collisions and mergers rises dramatically. Stars that form in close proximity do not simply coexist. They interact gravitationally, exchange mass, and in the densest cases, undergo runaway collisions in which successive mergers drive the formation of progressively more massive objects. Runaway stellar collisions. In a region the size of a molecular cloud, in a galaxy 280 million years old. The endpoint of runaway stellar collisions in dense cluster environments, according to theoretical models developed over the past 2 decades, is precisely the class of object invoked to explain MOMZ14's nitrogen signature, a supermassive star, assembled not from the gravitational collapse of a single gas cloud, but from the accumulated mass of hundreds or thousands of individual stellar mergers, growing progressively more massive until it reaches tens of thousands of solar masses and begins burning its hydrogen through the hot CNO cycle at temperatures and luminosities that dwarf anything achievable by normal stellar physics. That star, if it existed inside MOMZ14, would have been the brightest single object in the universe at the time its light was emitted. A stellar furnace of 10,000 solar masses fusing hydrogen at core temperatures of approximately 200 million Kelvin, its luminosity approaching the Eddington limit, the theoretical maximum luminosity at which radiation pressure exactly balances the inward pull of gravity for an object of its mass. Above the Eddington limit, the star would begin shedding mass in powerful, radiatively driven winds, enriching the surrounding interstellar medium with the CNO-processed nitrogen it was generating in its core in real time. Below it, it would sit at the edge of gravitational instability for the duration of its short life, burning itself out in a few million years before collapsing directly to a black hole of comparable mass. A black hole seeded from a supermassive star. In a galaxy 280 million years old. At a redshift where every reionization model predicts 100% neutral hydrogen in the surrounding intergalactic medium, and where MOMZ14's spectrum shows no strong damping wing. The neutral hydrogen is not there. The reionization bubble around MOMZ14 was already cleared. The reionization of the universe is one of the major phase transitions in cosmic history. After the formation of neutral hydrogen at recombination, approximately 380,000 years after the Big Bang, the intergalactic medium remained neutral through the cosmic dark ages. The first stars and galaxies, forming several hundred million years later, began emitting ionizing ultraviolet radiation, photons with sufficient energy to strip electrons from hydrogen atoms. These photons punched expanding bubbles of ionized gas into the surrounding neutral medium. Over hundreds of millions of years, those bubbles grew and merged until, by approximately 1 billion years after the Big Bang, the intergalactic medium was fully ionized, the state it remains in today. The timeline of reionization is constrained by multiple independent lines of evidence. The opacity of quasar spectra at different redshifts, the damping wing profiles of high redshift galaxies, the polarization of the cosmic microwave background. Those constraints converge on a picture in which the intergalactic medium at redshift 14 is overwhelmingly neutral, a nearly unbroken ocean of neutral hydrogen through which the first isolated ionizing sources were only beginning to carve their earliest, smallest bubbles. MOMZ14's spectrum tells a different story about its immediate environment. The absence of a strong neutral hydrogen damping wing in its spectrum, the spectral feature that would be imprinted by a surrounding neutral medium absorbing the galaxy's ionizing photons, is statistically significant. The gas immediately surrounding MOMZ14 was already sufficiently ionized at redshift 14.44 that its damping wing signature is suppressed below what every current reionization model predicts for that epoch. The most natural explanation is that MOMZ14 itself, or a dense surrounding population of similar compact luminous objects clustered in its protocluster environment, had already been ionizing its local intergalactic medium for a sustained period before the moment at which Webb captured its light. For the ionized bubble to be large enough to suppress the damping wing at the observed level, the ionizing radiation must have been running for at minimum several tens of millions of years. which means the stellar populations responsible for that radiation must have been actively forming stars and emitting ultraviolet photons continuously since the universe was perhaps 230 or 240 million years old. 230 million years after the Big Bang. Star formation, ionizing radiation, chemical enrichment. The Standard Model's timeline for the onset of star formation and reionization was not designed to accommodate this. Its predictions place the onset of significant reionization substantially later. The implication of MOM-Z14's ionized bubble is that either this specific region of the universe was anomalously, exceptionally early in its evolution, a 3 sigma or greater outlier in the cosmic distribution of first-light objects, or that the onset of star formation and reionization across the universe generally was earlier than the Standard Model predicts. Both possibilities demand a physical explanation that the current framework cannot provide from within itself. The Cersic index of MOM-Z14, derived from the Forceful morphological fitting, is 1.0. A Cersic index of 1 corresponds to an exponential light profile, the same profile characteristic of the disks of late-type spiral galaxies in the modern universe, and also characteristic of the stellar distributions in the outer regions of globular clusters. It is not the centrally concentrated high Cersic profile typical of early-type elliptical galaxies or the compact remnant systems seen in some other high redshift objects. MOM-Z14's light is distributed in an exponential profile across its 150 parsec body, consistent with a system whose stars are distributed throughout a dense but structurally organized cluster, rather than concentrated in a single nuclear cusp. This morphological detail matters because it constrains the evolutionary pathway. A galaxy with an exponential light profile at redshift 14.44 is not a random aggregation of primordial gas clumps. It is a structured system. Its stars are organized. The physics of gravitational relaxation, the process by which an ensemble of gravitating bodies evolves toward a smooth, stable distribution, requires time to produce that organization. Time that, at redshift 14.44, has barely elapsed since the Big Bang. Structure without time to build it. Chemistry without generations to produce it. Luminosity without mass to sustain it. An ionized bubble without an extended history of radiation to create it. MOM-Z14 is not a single anomaly that can be set aside. It is a convergence point. The location in observational space where multiple independent violations of the Standard Model overlap in a single, spectroscopically confirmed, morphologically resolved object. Astronomers have been presenting individual Webb detections at conferences and in preprints since 2022, each one individually surprising, collectively forming a pattern. MOM-Z14 is the point at which the pattern crystallized into something that the community can no longer characterize as marginal tension or modeling uncertainty. As the Sky and Telescope report noted, it was frankly pretty naive of astronomers to have assumed that star formation processes in the early universe operated identically to those in the modern universe, given vastly different environmental conditions. Higher gas densities, higher temperatures, higher turbulent velocities, the absence of metal coolants, the dominance of radiation from nearby massive stars. The early universe was not a scaled-down version of the modern universe. It was a fundamentally different physical environment, and MOM-Z14 is the most unambiguous demonstration yet that the physics operative in that environment produced outcomes the Standard Model was not built to capture. 45 researchers, hundreds of hours of observing time, one galaxy 280 million years after the Big Bang. A galaxy whose stars burn inside a volume the size of a single molecular cloud in the Milky Way, forging nitrogen with the violence of supermassive stellar furnaces, punching ionized light into a universe that was supposed to be dark, at a redshift so extreme that the photons carrying its spectrum spent 13.5 billion years crossing the expanding space between its stellar nurseries and the gold-coated mirror of a telescope orbiting 1.5 million kilometers from Earth. 13.5 billion years in transit, 280 million years at the source. The light is 13.5 billion years old. The event it records lasted, at most, a few million years. The lifetime of the supermassive stars that may have powered the galaxy's extraordinary luminosity and chemistry before collapsing, silently, into the black holes that may anchor MOM Z14's descendants billions of years from now. In the data returned by NIRSpec, that entire history, the star formation, the nitrogen forging, the ionization, the collapse, is compressed into a single spectrum. A pattern of peaks and troughs in infrared light stretched across a detector the size of a dining table, in a telescope drifting silently through empty space 1,000,000 miles from every human being who has ever lived. The universe does not care whether its structure is convenient for our models. It only emits light. It is our instruments, and our willingness to follow that light into contradiction that turns the inconvenient into understanding. There is an old observational limit that defined astronomy for most of its modern history. It was not set by the quality of mirrors, or the sensitivity of detectors, or the funding cycles of space agencies. It was set by physics itself. The limit is the surface of last scattering, the boundary in time from which the cosmic microwave background radiation was emitted, approximately 380,000 years after the Big Bang. Before that moment, the universe was opaque. No photon of light from an earlier epoch can ever reach us. The first 380,000 years of cosmic history are, and will forever remain, hidden behind a wall of thermal radiation that no telescope of any design, using any technology, operating at any wavelength, can penetrate. That is the hard horizon, the absolute limit of what electromagnetic observation can reveal. MOM Z14 exists at 280 million years after the Big Bang, a universe that had cleared its primordial fog 100,000 years before MOM Z14's light was emitted, leaving nearly 280 million years of completely open, observable cosmic history between the surface of last scattering and the epoch Webb is now routinely probing. 280 million years of cosmic time that are, in principle, fully transparent to infrared light. The hard horizon has not been approached. Webb is not operating at the limits of what physics allows. It is operating at the limits of what engineering and sensitivity currently permit, and it is finding, in that scientifically accessible volume, objects that should not exist. This distinction matters profoundly. The fact that the observed universe violates the predictions of the standard model in this regime is not a statement about the limits of observation. It is a statement about the limits of the theory. The universe is not hiding its early structure behind any physical veil. It is displaying that structure openly in photons that have been traveling for 13.5 billion years to reach a detector built by human hands. The structure is there. The theory failed to predict it. Those are two separate facts, and conflating them, treating the failure of the model as a mystery of nature rather than a failure of the model, would be a scientific error. The model is wrong. The universe is not mysterious. It is explicit. What does it mean, in practical scientific terms, to say that the standard model is wrong? It does not mean that lambda CDM is useless. The framework has extraordinary predictive power across enormous ranges of scale and cosmic time. It correctly predicts the temperature anisotropies in the cosmic microwave background to parts per million. It correctly predicts the abundance of light elements produced in the first 3 minutes of cosmic time through Big Bang nucleosynthesis, the hydrogen to helium mass ratio of approximately 3:1 that is measured identically in the oldest and most chemically primitive stellar systems in the universe. It correctly predicts the large-scale structure of the cosmic web, the clustering statistics of galaxy distributions across hundreds of millions of light years, and the relationship between the expansion rate of the universe and its matter and energy content. These are not minor achievements. They represent the most precisely tested quantitative framework in the history of science, tested against independent observations across 12 orders of magnitude in physical scale and nearly 14 billion years of cosmic time. What lambda CDM does not correctly predict is what happened in the first few 100 million years of cosmic time at the scales of individual galaxy formation. That is a specific, bounded regime, and it is precisely the regime that Webb, for the first time in history, has the observational power to probe directly. The framework's extraordinary success at large scales does not protect it from failure at small scales in early times. And the failure at early times is now observationally established with sufficient confidence that the community can no longer attribute it to modeling uncertainty or statistical noise. The revision that is coming is not the abolition of cosmology. It is the refinement of it. The the same process by which Newtonian mechanics was not abolished by general relativity, but subsumed into it as a limiting case, valid at low velocities and weak gravitational fields. Lambda CDM will survive, in some form, as the large-scale limit of whatever framework eventually accounts for MOMZ14. The physics of inflation, the existence of dark matter, the reality of cosmic expansion driven by dark energy, none of these foundational elements are threatened by the discovery of an unexpectedly luminous, nitrogen-enriched galaxy at redshift 14.44. What is threatened is the specific, tractable, quantitative description of how the first stars and galaxies formed from the primordial conditions that Lambda CDM itself correctly predicts. That is the seam in the framework, and MOMZ14 is the instrument that exposed it. The researchers who will close that seam are, in many cases, already working on it. Pascal Oesch at the University of Geneva is co-leading the Cosmos Web survey that found MOMZ14. Yijia Li at Pennsylvania State University, a graduate student who contributed to the discovery team, described this as an incredibly exciting time, with Webb revealing the early universe like never before and showing how much there still is to discover. Rohan Naidu at MIT, who led the team of 45 co-discoverers, has stated plainly that Webb is showing something that looks nothing like what was predicted, and that this is both challenging and exciting. That pairing, challenging and exciting, is the precise emotional signature of a science at a genuine inflection point. Not the manufactured excitement of a press release, but the specific intellectual discomfort of a community that built a rigorous, internally consistent, empirically validated framework, deployed the most powerful observational instrument in history to test it at its frontier, and found the frontier populated with objects the framework prohibited. The Nancy Grace Roman Space Telescope, currently in advanced development, will extend what Webb has begun. With a field of view approximately 100 times larger than Webb's NIRCam, Roman will conduct wide-field infrared surveys covering hundreds of square degrees of sky, transforming the handful of confirmed extreme redshift galaxies that Webb has found into a statistical ensemble large enough to directly constrain the competing theoretical models. If the current excess of luminous early galaxies is real and systematic, and every current indication suggests it is, Roman will find thousands of them, map their distribution across the cosmic web, measure their clustering statistics, and provide the observational leverage needed to distinguish between the competing theoretical explanations. Modified star formation efficiency, early dark energy, primordial black hole seeds, supermassive stellar populations, or some combination of all of them. The extremely large telescope, currently under construction in the Atacama Desert of Chile, will provide the spectroscopic follow-up capability to characterize these objects in chemical detail, measuring the abundance ratios of multiple elements simultaneously in early galaxies, building the chemical evolutionary record of the first billion years of cosmic time with a precision that Webb's current spectroscopic capacity cannot match. Its primary mirror, 39 meters in diameter, will collect more light per unit time than all existing ground-based telescopes combined. The observational infrastructure being built in the 21st century was not designed to confirm what was already known. It was designed precisely to find what is currently unknown, to go to the places where the theory runs out and measure what is actually there. MOMZ14 is what is actually there. The Milky Way galaxy is, in one specific and physically meaningful sense, a fossil. Its oldest stellar populations, the metal-poor stars in the galactic halo, the ancient red giants in globular clusters like Omega Centauri and M4, are the surviving remnants of the same processes that Webb is now observing directly in MOMZ14. They formed in the same epoch. They carry the same chemical signatures, the nitrogen enrichment, the alpha element enhancement, the helium overabundance, that NIRSpec detected in a galaxy 13.5 billion light-years away. The connection is not metaphorical. It is chemical, quantitative, and direct. The stars in Omega Centauri were enriched by the same class of stellar polluters, potentially including supermassive stars, that are being invoked to explain MOMZ14's spectrum. The physical process that built the oldest objects in our own galaxy may be directly observable for the first time in the spectrum of a galaxy at redshift 14.44. Two lines of evidence, one drawn from spectroscopy of individual ancient stars in our own galactic neighborhood, accumulated over decades of patient high-resolution observation, and one drawn from the infrared spectrum of a galaxy 13.5 billion light-years away, are converging on the same physical mechanism at the same epoch of cosmic time. The Milky Way is not external to this story, it is a participant in it. Every atom of nitrogen and every amino acid in every cell of every living organism on Earth was forged in a stellar core, scattered by a stellar death, incorporated into a molecular cloud, collapsed into a new star, and eventually incorporated into the solar system's chemistry at the moment of the sun's formation 4.6 billion years ago. The chain of nuclear reactions that produced that nitrogen began with hydrogen and helium in stars that lived and died in the first few 100 million years of cosmic history. Precisely the epoch that MOMZ-14 is now revealing, directly and in detail, for the first time. The nitrogen in MOMZ-14 is not alien chemistry observed at an incomprehensible remove. It is the same element, produced by the same nuclear physics, that makes life on Earth chemically possible. The early universe is not a separate subject from the one that concerns us most intimately. It is the first chapter of the same physical story. And we are reading that chapter, in real time, in the data returned by a 6.5-meter gold-coated mirror drifting silently at the gravitational balance point between the Earth and the darkness beyond. Rohan Naidu's words, published in the January 26, 2026 paper that announced MOMZ-14 to the scientific community, require no embellishment. With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted. That sentence contains the entire history and the entire future of the field in 16 words. It contains the confidence of a confirmed detection, the honesty of a violated prediction, the discipline of a scientist who does not confuse surprise with failure or anomaly with error, and beneath it, unmistakably, the recognition that the universe, in its oldest, most distant, most extreme observable chapter, is not simpler than the models assumed. It is stranger, more structured, more chemically violent, more luminous, more active, more alive, in the sense that physics uses that word, than the standard model was built to accommodate. The light from MOMZ-14 left its source when the universe was 280 million years old. It traveled for 13.5 billion years through expanding space, through the ionized intergalactic medium of cosmic ionization, through the large-scale structure of the cosmic web, past galaxy clusters and filaments and voids, arriving finally at the gold mirror of the James Webb Space Telescope in April of 2025, where NIRSpec dispersed it across a detector, and a team of 45 researchers read its chemical signature and confirmed what it was. 13.5 billion years of uninterrupted travel, a journey spanning nearly the entire age of the universe, and at the end of it, a number, a redshift, a nitrogen line, enough to rewrite what we thought we knew about the beginning of everything.